So David, can you hear me?
Yes, I can hear you.
Okay, great. So our next talk is by David Picado. It will be Deep Learning in Manufacturing. So David Picado is PhD in Mathematics and Specialist in Artificial Intelligence by the University of Manchester. He's been, during his career, more than 15 years long, he's been working both in academia and industry, and he has been involved in research projects, leadership combined with innovation teams. And after being director of data science in IT companies, he's now CTO of BitMetrics. So now, David, I give you the role of presenter, so you can show us your presentation.
So I can
Thank you very much.
Thank you. Thanks to you. Okay. So let's see. Here it is. All right. Can you see?
Yes. Yeah, perfectly.
Okay. First of all, thank you very much to the organizers, to Alex and Sergio, for inviting me to be here presenting this very brief talk, 20 minutes. And also thank you to all of you who are listening today. Well, I was already presented, but, well, as we said, my name is David. I work as a data scientist, as a mathematician at BitMetrics. I'm also the co-founder of this company. And what we essentially do, data solutions. We work on data solutions, mostly related to deep learning, mostly related to computer vision, but not only. And, well, so that's what I'm going to talk about today, computer vision in general. Okay, first thing to say, my talk is going to be very high level. It's meant for those who know basically nothing or not much about deep learning. I'm not going to explain very deep things. I'm not going to explain very deep concepts. So, I mean, if you know a lot, maybe you get bored. Sorry about that. Maybe also I will repeat some things that you heard in the previous talks, but that's, I guess, inevitable. So, well, let's get started. I'll get started with just a very brief definition of what deep learning is. Yeah. Deep learning is artificial neural network-based learning process that essentially uses two or more hidden layers to process inputs and extract high-level features from raw inputs. So what do we mean by all this? Well, if we focus, if we stick to the most general sort of learning method, which is supervised learning, so we have some inputs for which we know the ground truth, we know the labels. Inputs can be images, can be text, can be all sorts, variable from tabular data, etc. And labels, well, it depends on the kind of problem that we're tackling. We talk about classification labels of these inputs, classification of images, label of these inputs. Their images will be, for example, categories. If we talk about regression, for example, it will be numbers in the continuous space. If we talk about object detection, for example, it will be also categories plus the bounding box surrounding these objects belong to these categories. For segmentation, we will need something like a mask that interprets, that classifies every pixel in the picture. If we talk about language generation, then it's a word. Yeah? The label would be the next word, the word that follows the piece of text that we enter as an input. So essentially what we do is process the input through some sort of, well, not some sort of, through mathematical operations that we, in this very small representation, formalize as functions. In this case, we have two hidden layers, two functions, F1 and F2, that perform some mathematical operations on the input. And in the end, from the input, through these mathematical operations, we output a value, these functions have parameters, and the learning process is actually about learning these parameters of these functions. And how do we do that? Well, first we need some sort of loss function. We need a way to compare the ground truth, that is the real label annotation, with the annotation produced by the network in its iterative steps. Well, if it's, for example, classification, this function could be gross entropy. If it's regression, it could be the mean squared error, etc. Then with loss, we sort of try to identify how responsible each parameter is of this loss. Yeah? And we do this by differentiating. And we take this loss function and differentiate by each parameter. And then we backpropagate this error through, in the most typical way, stochastic gradient descent. In general, it's something like we update the values of the parameters in a way like the parameter a at time t plus 1 equals the parameter a at times t plus minus lambda, which is the learning rate, times this derivative that we got from this loss function. So essentially, it is this. The idea we have to keep is that we're trying to learn some parameters of some mathematical functions in order to fit them all, just to produce in an iterative manner an output that's closer as we go to the ground truth. It's essentially that. So, right, if we talk about, in particular, just to see what these features that we're generating at each, let's say, stage, at each level, if we talk about computer vision in particular, or about convolutions, so after each convolutional layer, which is not necessarily just a convolution, convolution, just to simplify, is some sort of it's something that can be expressed as a matrix multiplication, and let's leave it there. It's a mathematical operation. So after this operation, we transform the input, and we get somehow features. We go from, as we go deeper in the net, we get higher level features. So in the first layers, we get, I don't know if you can see this image properly, we get very simple features. We extract features as simple as, for example, some circles, some straight lines, some corners, things like this. And in further layers, we play with these basic features, with these features that we've been generating previously, to generate more complex features. Yeah. We use the image on the right, which is a toy example from by Isole. For example, in this first layer, we're getting very simple features. Then in a further layer convolution, we get higher level features that get from this sort of composition of similar features. And in the end, this example is for classification. So from these higher level features, we perform classification. Traditional methods, deep learning in traditional methods, all these feature extraction, feature engineering would be done by hand, by an expert, let's say. Deep learning, all this feature extraction is somehow done automatically. Okay. So deep learning, deep learning is definitely the main learning method, essentially, in image processing, computer vision, and natural language processing. And it's in these fields, it's the performance in these fields that gives deep learning its reputation. But, okay, lately, deep learning has also been used with different types of data, for which traditionally different types of learning processes, learning methodologies have done better or have done very, very well, like gradient boosting machines or random forests. And here there is an example. For example, probably you know Kaggle. Kaggle is a competition platform where there are, let's say, they present data challenges. It's extremely competitive. Kaggle is actually a reference for, if you want to know what's the latest successful methodology in data science, you look at Kaggle. You go through competitions, check the solutions, and that's top. I mean, most researchers and practitioners of data science actually are there, compete, and prove the methodology in some of those challenges. And for example, in data set which was not officially, let's say, suitable for data for deep learning, which is time series data. Some guys used deep learning without any domain-specific feature engineering, without doing much in the data, maybe something with the time variables. They put time as variables, as categories, as tabular data, and they got third. They didn't win, but they got third, and then that's an amazing result. It's an amazing result. So deep learning is definitely mostly related to image processing, natural language processing, but not only. It does well also with other types of data in other fields. Well, deep learning is not new. Here I have put some milestones. For example, this backpropagation method, which is very essential to deep learning, dates back to the 60s. Convolution, the first convolutional work dates back to 1979. So it's been a long time since then. And for example, 1989, Jan LeCun, this is a good benchmark, brings together these two concepts: convolutional neural networks plus backpropagation, long short-term memory for natural language processing. It may look all time series data. It may look like a very novel sort of thing, but it's not so. It's from 1997. Some other important benchmarks in deep learning, of course. 1999, huge development of GPUs. Those developments increased speed by 1,000 times, something like that, with respect to GPUs. And this is important. 2009 for data science, for deep learning in particular, the ImageNet database. This is a great thing, actually. This changed many things in data science, in deep learning. It's ImageNet is a data set that contains something like 14 million images. At the beginning of the label, it's with the effort of many people that they were progressively annotated in different ways. Sometimes, categories. Also, now there's also a subset of those images that has bounding box annotations for object detection. So this is a very important data set on which there is a competition, which I will talk about in further slides. More recently, of course, some very important things that led to a huge development in deep learning. It's in connection with the last thing that I mentioned, this creation of publicly available annotated data sets. That's extremely important, just to try new methodology to build an algorithm. You want to try it. Well, there are data that are labeled. Labeling is a pain. It is a labor-intensive task. Doing it well is also difficult sometimes. But nowadays there are many data sets labeled, maintained also by several institutions, sometimes universities, sometimes all sorts of institutions, and very useful indeed. One example is ImageNet. We also have Pascal for object detection, Cocos for object detection, MNIST for character recognition, Candid for segmentation, IMDb for text, Wikipedia for text, all sorts. Together with this, the challenges that I mentioned before, for example, through Kaggle, there are lots of open competitions in which an awful lot of people get involved, and that helps an awful lot in actually improving everything about data science, and particularly what people think. GPUs, also very important bit when it comes to deep learning. So yeah, current GPUs in the NVIDIA series, you can have one of these graphical processing units in your laptop. You don't even need, not necessarily cloud services to do something really powerful and cheap, actually. They are not that expensive anymore. And then also this is, I guess, important for many of us, which is the creation of open source deep learning libraries like TensorFlow. They're all very recent, you know. You can see here the dates, the initial release. The oldest is Diano from 2007, but the others, the most known, which are probably TensorFlow, Keras, and PyTorch, all from 2015, 2016. They simplify an awful lot. They help an awful lot in simplifying deep learning programming, basically. Right, just to give an image of perspective of what DIA has achieved today. Back to this example that I mentioned before, ImageNet, in particular about this competition, ImageNet Large Scale Visual Recognition Challenge. It's a classification and location challenge. It starts on its classification in 2010. If we focus on classification, the task is as follows. We are given 1.2 million images for training and 150,000 for evaluation. Those are fixed sets. The ground truth is a single category. It's the category of the main object that's featured in the image. And the challenge is to build an algorithm that predicts 5 categories sorted by descending order, and there are 1,000 possible categories, non-overlapping categories. Like, for example, if you have mammal, you will not have dog, because it's like a subcategory of mammal, for example. Accuracy is measured in the two-level ground truth of the image within the 5 predicted categories. Then accuracy 1, well, that's positive. If it isn't, negative. And the results, you can see, I mean, it's amazing. It's in the first years of the competition, the methods were based on what we could call shallow learning, a bit of what I said before. There is in these solutions an awful lot of manual feature engineering, and it's AlexNet, the first sort of deep learning solution that sets this benchmark, and it brings a lot of people into, let's say, deep learning. AlexNet generates an awful lot of interest in convolutional neural networks. While there is here a mark, you can see this sort of human performance. This is some, you can read this paper to see how it is calculated. It's some sort of average survey on how humans perform. Yeah. If we take it as reference, and we see that the last years we are actually better than these solutions to both these years are better than human performance. But take this shallowly, I mean, this human performance. In the end, these levels are, these images are labeled by humans. So, well, some other examples, if you check the news every now and then, you will see news like this, like, well, some algorithm, some algorithm based on deep learning has been doctors in the prediction, in this case in particular, is in the prediction of brain tumor. The machine scored, the algorithm scored 87% accuracy against a team of doctors who scored 66% accuracy. There are many examples like those in the news. So that somehow gives an idea of how well in this field, in computer vision, deep learning is doing. It's actually at a very, very, very high level. So if we focus a bit more in, let's say, these problems that we can come across if we talk about industry, about manufacturing, or in general, we'll have some typical examples. One of them is classification of images into one or several categories. If we talk about quality inspection, quality control, for example, labels, good, bad. In this case, it's biscuits, good, broken. Yeah. Localization. This is different type of problem. It's based on regression. Localization of some particular landmarks. We don't mean to mark here all the elements of a particular category, but just one or some elements that are of interest to us. In this case, well, we selected this screw in this sort of front plate. In the image, there are other screws that we're not interested in. If you see on the left picture, there are also some other screws here. Those we're not interested in. We are interested in these ones. The level for learning here will be the coordinates of this screw. Then we have segmentation, which is classification, but it's pixel classification, meaning we have to classify every pixel in the image. Labels are these labels are quite expensive to generate. We need to generate masks like this that you see on the left, on the right hand side. So for each image in the training set, we need the corresponding mask to train. And object detection, which is classification on the one hand plus location. Location here we define as this sort of square box that surrounds, as well as possible, the object that's classified within it. Right, computer vision, just a very brief remark. We're not talking only about photos. Phosphorus from, for example, visual spectrum or other ranges of the spectrum. Any data representation that can be reduced as digital to digital image, something like a matrix with numbers 0 from 0 to 2.5 different channels, that's fine. For example, the picture on the left is sound. This is a spectrum. We represent sound as an image. Image in terms of frequency, amplitude, and time. The color is the amplitude, frequency, the y-axis, the time is the x-axis. And the one on the right is an example that I don't understand very well, but it has to do with some point series that I don't know exactly what represents. This example I got when reading about fast theory. But it's something about cancer, yeah. And by analyzing this, analyzing these pictures, these images generated from this data, one can somehow predict, yeah, the presence or absence of this type of cancer. Right, about models or architectures to perform these tasks that we just mentioned. Well, there's several I will just mention a few. A well-known one is BGG. This one won the competition, I think, in the competition in 1914. Sorry, 2013, 2014, don't remember. Well, it's a series of convolution layers that in the end generate some sort of high-level feature map, which is the 7 by 7 by 112, and then we proceed to some sort of classification into 1,000 categories. This is the 1,000 categories of the ImageNet, yeah? Which was trained on ImageNet original. These kind of structures we could use, for example, for these classification problems, for regression problems, localization problems. This one could be suitable. Not only this one, actually. I use mostly ResNet, which is something more recent, and it does not need that many parameters. For example, for segmentation, the kind of architectures models that are used are somehow of this type. It's the known encoder, decoder model. We have this encoder stage, which could be not necessarily this. It could be, for example, ResNet or PGG, the one we saw before. Basically, we do a first stage of feature extraction, and then we upsample, so somehow classify from that feature extraction every pixel into each category. I cannot go into much detail about just the idea is that it's first we code the features, and then from there we try to somehow recover the size of the original image by the convolution, sort of, and get every pixel classified by the right category. And then for object detection, there is YOLO, there is one. This one probably works a bit better than YOLO. Maybe slower. It's a one-stage model. It has a backbone, which is common to the two, let's say, previous ones. This could be RosNet, this could be VGG. There is this backbone that extracts features. Then we have this sort of feature pyramid net that somehow extracts features from this backbone at different resolutions. So we get different resolution maps, feature maps. And then from each feature map, we will have a classifier and a regressor. The classifier is just is to classify the box as it has an object or it doesn't, and if it has, which object it has, which category it has, and the regressor, which is essentially for numbers, just to assess the bounding box. The way it goes is when we train, we sort of generate candidate boxes, which we call anchors. And through this process, we try to determine first if this anchor contains an object, and if it contains one, which one it is, and then adjust the anchor to a real bounding box if it contains an object. Adjust the anchor to contain very precisely, to stick very precisely to just to this object. We're classifying with it. So, right, is DL affordable? What do I mean by this? Okay, we have, through all research in the previous years, we have amazing data structures, the data architectures that are able to perform very well to solve these tasks that we mentioned, these problems that we mentioned. But, of course, they require some computational power, and they have an amazing number of parameters. Don't remember, but I would say that it's somewhere here. VGG, I think, has 130 million, and ResNet 50 has like 25 million parameters. That's an awful lot of parameters, meaning potentially we will need an incredible amount of images just to be able to fit a model. Well, not if we use transfer learning, and that's the sort of solution that we have for this problem. Is DL affordable? Well, computational power, I would say yes. Nowadays, with this, we can perform powerful computations even with non-cloud, like I said before, with GPUs that are available for very little money. And in order to overcome the problem of the amount of parameters that we need to train, that we need to learn, we have what we call transfer learning, and you probably saw some of these examples in the previous talks that I could not attend. That's why I said you probably saw some of the examples. Very general idea. It's we can use a pre-trained model. That's simple. For example, if we take this model that we presented before, this VGG architecture, we can retrain it on ImageNet. We don't actually have to. I mean, you can download the weights from PyTorch, I guess, anywhere from well, very many places, so it's no problem. And so, for example, what we would do here is preserve the weights of all these layers, so you see across. We freeze these layers. We release this one. For example, if our problem has to do with classification and it has to do with 5 categories, we could replace this last layer with just a fully connected layer with just 5 categories. It doesn't need to be strictly so. We can release any other layers that we want. That doesn't matter. general idea is that we get the weights that have been pre-trained on a different set, and we train just from scratch, from fresh, just a few layers. We do a few runs, we train these few layers with new weights, and then we fine-tune the whole net. We increase the whole net and do a few more runs with suitable learning rates and train all the weights, basically. And this is, well, of course, basically because when you train on ImageNet, you learn all sorts of features, low-level, high-level features, almost no matter what class of classification you have to deal with. Probably among those, at least low-level features, there will be some that will be useful for your classification. I talk here about classification, it's the same about regression. We also can talk about whatever, object detection or location or segmentation. For example, segmentation, we could freeze this bit, we could use ImageNet or PGG. We freeze at the stage of the training this bit. We learn from scratch the weights related to this, maybe on a simplified version of the net. And then we freeze these bits, this weight here, and fine-tune the whole thing with very few images. That is the idea, that if we do so, we need very few images. Some examples of these very trivial examples. For example, this is an object detection. There is a single category here. It's nothing too complicated, but the relevant thing is that we did pretty well, actually very well, with only 146 images. It's just about detecting these stones. It's not a very difficult example, but 146 images. It's very little. This one is similar. This is about segmentation. This is probably more difficult, but still, only 116 samples with a cross entropy of 0.0241. This is a very small. This had as a basis the ResNet trained on ImageNet. This was RetinaNet trained on Coco, which is set. And this is another example. This is regression. This was same ImageNet. And only 136 samples. And the mean squared error, which is ridiculously low. So, well, essentially, this is what I wanted to explain. Something very brief, just about simple ideas, and in particular, these transfer-learning single lakes. I would say deep learning very affordable, actually quite easy to implement for many problems. Okay, this is all. Thank you.
Fantastic, David. Thank you very much for your talk. It was very, very enlightening. And I have here a couple of questions from Ismael. So one is very technical and one is more general. Let me start with the more general one. So he asks why the use of artificial neural networks involves setting a certain structure, most of times manually. So what do you mean by shallow learning in the context of deep learning?
Oh, shallow learning? No, shallow learning is typical something like perceptron nets. It's nets that have a single hidden layer, just a single. Something generally linear. Also,
so it's just a perceptron.
This is, yeah, it can be more complicated than that, but yes, generally linear models with a single layer. Yes. Okay. Thank you. And the second question is. Well, okay. I was about. Sorry, I was about to. In this input, one would use already features, specific features that one got through probably a lot of feature engineering. So basically, this network wouldn't learn the features, wouldn't extract the features.
Yep.
That you have to do. You have to find the right features to perform the right classification, the right regression, whatever. Yes.
Okay, and then the second question is, the steepest descent can be a rather slow gradient-based optimization algorithm.
Yes.
He's asking if it's possible to use another gradient-based algorithm to do the backpropagation.
Oh, yeah, of course. I mean, there are
like
several. In the last few years, there have been several improvements in the optimizer. What is mostly the Adam optimizer. Yeah, it's based, of course, on the same idea, on stochastic gradient descent that combines momentum and then also some sort of when you see that the learning rate is when you don't get much improvement in your objective function in the loss with the actual deep learning learning rate, you somehow update it dynamically.
I see.
Yeah, I mean, there are lots of optimizers.
I can imagine that the amount of terminology and different variables, different libraries you can use, functions.
Yes, and the optimizer, normally when learning, you set strategy to define the learning rate. It's generally dynamic. It depends on the epoch in which you're training. So yeah, it can get complicated, yes.
Okay, and I have a final question for you. With this, I see that in most cases here, the ones you presented, you are using already available neural networks, right? And all this. I think from the industrial point of view, one of the key elements is to protect your software somehow, right? If you're using public libraries, public neural networks that are available there for everyone, how can you ensure that some other company can't just enter into the field and do exactly what you are doing with the same algorithm? How do you protect your know-how in this case?
Yeah, the point is that by building your own architecture, you're probably not gonna improve what other people have done and have published and made available for everyone. So is that there isn't much of a solution to this. You can use this to, I mean, it's this part of the model that you use is not the whole model. Then there are some extra layers, and you can modify it, I would say substantially by ways. But no, in this case, there is no, in that part, there is no industrial protection possible, no. Okay,
see. But it's something to keep in mind, probably, to modify your network as much as you can and don't give many details. Okay. if your aim is to protect all this technology. So thank you very much, David, again for the
thanks to you
presentation, and thanks